Okay, welcome everybody to another course in numerical algebraic geometry. We're continuing our section on univariate homotopy continuation. Just to remind you of the setting here, we have a polynomial in one variable that we'd like to solve. And by solve, we mean find approximate solutions. So find approximations of the real and imaginary parts of the complex numbers, which are the solutions. So this guy here lives in this polynomial ring, and to solve this, we are going to construct a much easier polynomial to solve of the same degree, just x to the d minus 1. Its solutions are the dth roots of unity in the complex plane. We can write those down pretty explicitly. Okay, well that's all well and good, but that's not the problem we're trying to solve. G is not the problem we're trying to solve, F is. So we need to somehow deform in this direction, and we do so via homotopy. So we introduce a new time parameter. And we construct this convex combination times 2. Okay. And when we do this, we get a result that says there are only finitely many t values for which the specified system H has a multiple root. So we definitely don't have multiple roots over here. These are the dth roots of unity. Okay. But at some values between t equals 1 and t equals 0, it's possible we have multiple root at some complex t values. But it's only going to happen at finitely many. So popping out this real picture, so this is a real line segment, we're going to pop it out into a copy of the complex plane. I usually put the variable as a subscript just to remind us like what space we're living in. So what I've drawn on the board is this line segment from 1 in the complex plane to 0 in the complex plane. And we might have some points, some t values, for which the univariate polynomial in x that I get when I replace t with that t value has a multiple root. So far so good? Okay, so that's gonna be a big problem. We'll see why that becomes a problem today. But right now I'm simply promising you it's a problem. And the solution is that we are going to move in a random circular arc here from 0 to 1. Okay. Such arcs can be parameterized. I'll just say it's p gamma that goes from 0 to 1. Tau gamma 0 is say 0, and tau gamma 1 is 1. Okay, we're still going from 1 to 0. We've got this path we've parameterized, but we're going to go in some random circular arc that contains both of those. And as a result, this circular arc, this new path we're going across, is not going to touch any of those finitely many bad t values. Except at one point that there might be an exception, which is at 0. In other words, the polynomial we are trying to solve might have a multiple root. In which case, there's no way we're going to get a path that never has a multiple root. We need one at the end. That's the polynomial that we're trying to solve. And there's a calculation you can do, or you can look at the notes, that if you do this, you make this composition. So in other words, we're going to follow this homotopy not along this line segment here, but along this circular arc here. And you simplify, you get that this looks like 1 minus t times f plus gamma times t times g. Where again, the definition of tau gamma, check in the notes for the exact description of exactly how you parameterize these circular arcs. Okay. And I think, if I remember correctly, there's a big constant out front, but it's not going to change the zeros. So that's great. Because what that means is that we're never going to encounter a situation where the solution paths here cross each other. This crossing means you have multiple. Except perhaps at the end.
Is by crossing, you don't mean intersecting.
I do mean intersecting.
You do.
Yeah. That's right. Great. So let's rigorize a little bit of this. We're actually following paths and they're smoother than their eyes. So whatever's going on upstairs, I'm just going to draw what I promise it looks like, but you should look at this with some doubt right now. So whatever these are, this is the zero set of H as a subset of C squared, or I'm thinking of C squared here as you have the X values across the T. These paths we're looking at, they are a graph. Give these names, x1, x2, x3, x4, and x5. Okay. So here there is no multiple root. It's a d through to d. Okay. Equivalently, this means the derivative of g doesn't vanish at any of these points. Remember, you have multiple root if and only if your polynomial vanishes and your derivative vanishes. So e dx g evaluated at any xi not equals. So that's the same thing as x h x1. Okay. So the implicit function theorem states that locally, so there's some interval around t equals 1 here, such that upstairs, since this derivative doesn't vanish, this is the graph of some function. Okay. Remember implicit function theorem? Maybe, maybe not, but that's the condition you need. And that's the result you get. You need this derivative to not be 0. And as a result, you can express the geometry of this solution set as locally the graph of a function. So there's some interval around 1, we're not saying how big it is, such that upstairs in some neighborhood, this is just the graph of some function from that interval upstairs. So now perhaps I've convinced you that if you zoom up a lot at this starting value, it looks like this curve that I've drawn and that I promised. Okay. Great. So now, instead of x1, I'm going to write x1 of t. This is some function. It's well defined near t equals 1. And since every point on here is a point in this variety, let's just do it with x1. Any point here is going to solve this system. Or t in some interval we have no information about right now, other than it contains one. Okay. Okay, so now we follow our nose here. So we can do things locally. We want to get things more globally. So we're just going to iterate this process. Well, we have to do it at an actual point. Let's see. Okay, so I have something well defined here on this open part of this curve. Can I get something defined here? Yeah, I can just take the limit here, right? And this will still hold because the limit of the left-hand side will factor through into the composition because everything's continuous because it's polynomial, and the right-hand side remains 0. Okay, so I can actually make this well defined on a closed interval by taking limits. What could I possibly lose in this process? What I might lose is that at this closed part, I might not have this non-vanishing derivative. That's the thing you should be concerned with. Okay. Because even though taking a limit here will still give me 0, this, so this derivative might be some function of t which actually does approach 0. Okay. Because the thing I want to do now is I want to apply implicit function theorem. That's only going to work if the derivative is not 0. Okay. Well, goody, we've already shown nothing in here has a multiple root, right? And that's exactly this condition that we can apply implicit function theorem. And this totally makes sense, right? So if we do have a crossing here and we zoom in, it doesn't look like the graph of any function. It looks like a cross, right? So you can't apply implicit function theorem. There's no well-defined path, even though our eyes will see these things cross and go, yeah, this one should go from up to down, this one should go from down to up. That's not necessarily the case. There actually is no well-defined way to continue. Okay, so we apply it now at this A value. We get some open set. We chug along, we start marching along this curve. This process is called analytic continuation. Okay, so now there should be a particular concern that some of you maybe have, which is that you might get some sort of Zeno's paradox situation, right? So like, what if the curve, looks like this, and t equals 0 is over here, right? Well, yeah, I can keep on applying implicit function theorem and closing it up, but I'm never going to get to this point, right? But the reason is because this point is a path crossing. At this point, the derivative, this corresponding derivative is 0. There's a multiple root, okay? So if you're concerned that the limit of this process stops sometime before t equals 0, give that infimum a name, call it A star, and then ask, does A star have a multiple root? Right, so here, concern. This whole process stops here at some x star A star. Okay, but we know it doesn't have a multiple root because we did this gamma trick. And so we can actually apply implicit function theorem here. So we will get something with positive length, which will gobble up that infinite number of steps that we thought we would have had to take. Okay. In particular, it contradicts the claim that this is the farthest we can go to the left, because we can go further by the implicit function theorem. Any questions on this process? So what's the idea? Implicit function theorem, it works at the beginning. You can take limits to stay along the path. And you've already proven that nothing on the path has a multiple root, except maybe at the end. So if you would stop this iterating process somewhere, well, call that A star, apply implicit function theorem there, you get a contradiction. You can actually go doesn't stop. Except maybe at t equals 0. Because we didn't make any promises at t equals 0. Okay. Conclusion from this whole discussion. There's smooth paths. Listen. Okay, so we can take their derivatives with respect to dx dt. Questions online? Huh? Good, great. I am going to keep this up now. Because that's you gonna erase? You just move that. Yeah. I'll just clean things up in the picture.
In that one. So I'm a bit confused, like, so is that supposed to be tau gamma t there in the white chart?
No. Well, that's the magic. Okay, so tau gamma is some function in t. Let me grab exactly what it is. We can work this out. We have the time. So this is defined. The t maps to t gamma over t gamma plus 1 minus. That's the parameters. Promise. Okay.
Yeah.
All right. And you can extract the real and imaginary parts and confirm that those lie on a circle, but it's a pretty tedious. Okay. All right. So what am I going to do? So let's plug it in. So we get h of x comma tau gamma t. What's it look? It looks like, well, 1 minus t gamma plus 1 minus t f plus t gamma over t gamma 1 minus t g. Good? Clear denominators. Okay.
Yeah.
This just becomes a t gamma g. This, the t gamma minus the t gamma kill each other off, and you're left with 1 minus t.
Yeah.
How neat is that? Isn't that great? So really just adding this complex number here follows this. It's a bit of a, I think this is like one of the cleanest simplifications in numerical algebra.
And the denominator stays, right?
The denominator, sorry, say again?
The denominator will be there, right?
No, we're clearing denominators. We're gonna multiply it. It's the whole c, I think.
Oh, right.
And C would be dependent on
C, some constant,
Oh,
some constant. The 0 set doesn't change the whole one.
Alright, so if I understand the process correctly, at t equals 1, we look at take any simple root, look at its neighborhood. There is a implicit function theorem which we can see that one neighborhood does not have any other repeated roots.
Not only that, but that neighborhood upstairs is a graph of a smooth function.
And then take that function, that path that we get, that need not be amongst the paths that we have using the homotopy, right? The paths that we get during the homotopy, so we trace that path along the homotopy path, right?
No, these XITs are the homotopy paths.
path. Okay.
Yeah, these are the solutions
All
over
right.
T. Yeah.
So and then at the end point when we reach towards, because since we just
We have no idea what to do at the end point yet.
so we just take the limit at that point and we extend that because
Oh, yes. Theoretically, yeah, you can just take the limit at the end point,
right.
and then you iterate implicit function theorem there. And your only concern is that you'll have some Zeno paradox where you're actually limiting to something that's strictly larger than 0.
Yeah.
But that doesn't happen because of the argument I made before. Because if there was such a limit, you could apply implicit function theorem there, and contradiction, you can actually go further towards.
So that's why that adjustment makes sense. Instead of going with h of x comma t, we are working with h of x of t gamma t. That is exactly why. Otherwise, there might be a multiple crossing, and then we would run into a problem.
Yeah, you actually get things like this. You get pictures like this if you were to graph it, right? And so there you can keep on going, keep on marching, but you're going to get a Zeno paradox, right?
Right.
You're going to just limit out right there. You're only going to keep on getting halfway closer to it. Okay. So that's a problem. Right. Okay. You can also think about this as I'm slicing, I have 2 real roots, because I'm drawing a real picture, 2 real roots, 2 real roots, 2 real roots. Here I have 1 real root with multiplicity, and here they split off into complex conjugates. So there's no way to assign one or the other of these in a well-defined way to one of the complex conjugates. These crossings really are not able to be resolved in some naive way like that. Okay, great. So the point is we got these xi(t)s. They are well-defined smooth paths. And so we can take their derivatives.
You get a differential equation, right?
That's where we're going. Yeah, we need a differential equation. So the best trick, well, when I took differential geometry, one of the best tricks was to take the derivative of 0. Okay, this seemed to always give something fruitful, and indeed it does here. This is 0. Let's take its derivative. Well, on one hand, we get 0. On the other hand, we're going to get a chain. Okay, a multivariate chain, right? So what's going on? So I have some CT goes to CX cross CT. And then that goes to see something we don't have a variable for yet. This map is t goes to x of xi of t comma t. This map is xt goes to h of xt. Okay. And this composition is 0. It's the 0 function from one variable to one variable. Okay. So its derivative is 0, but its derivative has to obey the chain rule because it's composition of functions. So what's the chain rule here? Well, first Jacobian is dxi dt comma 1. Right, this is the derivative of the first thing with respect to t, the derivative of the second thing with respect to t. And over here, pardon my shorthand, you get these partial limits. And this has to be 0. But on the other hand, just keep it. Well, what are we after? We're after this. Right, we want to get some differential information about these paths. Okay, so we can just solve for it. And this tells us dxi dt is negative ht. This is the chain. But it's a really cool application of the chain rule, so we get a whole new name. It's called the Davidenko differential equation. And that is called random. Okay. And this is the differential equation we're going to solve. Now, this is not a differential equations class. It's not many classes, right? It is just a numerical algebraic geometry class. But let's just follow our nose here. Let's say we're starting at a point, and I have some way to know how x is changing with respect to t. I have some differential information, which means, so I kind of know what this tangent line is, this path. So if I wanted to guess what happens at, so this is some t star value, and this is some t star plus h, where h is very small negative number. Okay, well, I can just guess that it's this. Right, that's a good guess. That's the best guess you have with first order differential information. Like provably, the tangent line is the best linear approximation of a curve at a point. This is the best you get. Okay. Using this fact to make this a guess is called doing an Euler step. And doing this over and over again is called Euler's method for solving first order differential equation. So let me. We're still good on board space? All kind of. Let's here. So we have some x star, t star. Approximate. And we have a differential equation depending on x and t, which gives us dx dt. I'm going to drop the subscripts of x. We're just going to focus on one path called x. When I write x as a function of t, I mean that path. Okay. Inconsistent. Okay, yeah, so an Euler step, apply to x star, t star. Well, I just need new x value. Let's put h here. So this is going to be x star plus h times phi of x star t star, comma t star plus h. I'm really just taking an h step along this line. We're going to code this, by the way. Good. And then we can iterate this process. So here we can pretend we're on the curve, even though now we're definitely not on the curve. And we can try to get the differential information there, which will be a little bit off because we're not on the curve. And we can iterate. And we'll accumulate this error over and over and over again. At the end, that could be actually a problem. Okay. So there's this thing we can do in between each Euler step to make our guess better. And some of you may have learned this in calculus, some of you may have not. I was taught this in calculus back in the day, and it's called Newton's method. Okay, so here's the idea. This is in quotes. So if you have an almost root to some continuous differentiable function, then you can adjust. I always forget if it's plus or minus. You almost have a root to a continuous differentiable function, then this is even better. On my what?
On your axis, or is that n
This is okay.
supposed to be replacing that?
So if you have almost a root, then I'm going to define a new number. It's going to be the almost root you had minus that function evaluated at that almost root divided by the derivative with respect to x of that function evaluated at that root.
Yeah.
So far so good. This is better. Okay. So starting at let's say an x naught in C, which is maybe what we're getting at, we can construct the sequence where we just iterate these Newton steps. It's called a Newton sequence. Okay. And as long as you are sufficiently close to a true root, this will converge to that root, and it will converge very fast. Okay. It's in the notes exactly how fast. It's called quadratic convergence. It basically means the error at the kth step is less than some constant multiple of the error at the previous step squared. Okay, so that's pretty strong. That's converging very fast. Okay, and there's a whole world of people who study the dynamics of Newton's method. Super cool. You get really nice pictures. Yeah, great, good. Okay. So what is the game then? The game is predict via Euler, correct via Newton. Predict via Euler, correct via Newton. If you're particularly pessimistic and cautious, do like 5 Newton iterations in between everything. Newton comes for free. This takes like no time on a computer to do. Okay. So great. Really good. Oh, you only get quadratic convergence toward the root if it's not a multiple root. Another fantastic reason to have avoided them in this process. Any questions? It's all up. So now for some language. So performing the prediction and the correcting step is over and over again is a predictor-corrector method. There are various predictor methods. You can use higher order differential information, and that's not particularly hard to extract. But they're more costly, but they're more accurate. But you got to ask yourself, how much accuracy do I need if I have this Newton step? Yeah, so one can study the trade-off in these computations and try to analyze it, and people do. Yeah, the only corrector method I ever use is Newton. That's going to be completely sufficient for this course. Okay, so the process of doing the predictor-corrector method along a start solution is called tracking that solution along the Homotopy path. The process of taking the polynomial system you want to solve, constructing a start system, constructing a homotopy, applying this gamma trick, and then finding all the start solutions, and for each one tracking using a predictor-corrector method is called homotopy continuation. Specifically, polynomial homotopy continuation. So while I was looking at my notes, I realized I did skip one important fact here. If this has distinct roots, then there is a bijection from the start solutions to the target solutions based on xi of 1 goes to xi of 0. In other words, we're not missing any solutions as we track all these paths. So that property is called accessibility. That would not be the case, for example, if I started with a smaller degree polynomial. Right, if I only had 3 roots and I was trying to find 5, I can't reach all of them. So that would be a homotopy that's not accessible.
I will be able to reach 3. Right?
You would be able to reach 3 with a start system of degree 5, but you wouldn't be able to go in the opposite direction. Use a start system of degree 3 to find the solutions of a polynomial of degree 5.
If we repeat this process, will we be able to?
Sorry, there is nothing to repeat.
Sorry, what?
Whoa, really?
Siri picked it up.
Oh, that was your iPad. I thought it was a Zoom. I'm like, that's wild. Okay, I feel old immediately. Y'all can go on YouTube and replay my reaction over
I don't know how it even started.
Okay. Great. Anyway, if I repeat what process?
Yeah, so if you repeat the process of having a lower degree polynomial here, and say sort of do it randomly enough, will you be able to hit all the roots?
Okay, that's a good question. Let me think. So first of all, I don't think there's any practical reason to do this. Let me say that.
Yeah.
But it's a good math question. Yes, because of monodromy, we'll get to it later. So Chronicles questions. I started with a polynomial of degree 3 because I didn't watch these lectures and follow the directions or something like this. And I tried to solve a polynomial of degree 5. I'm gonna get 3 of the solutions, but I'm gonna miss 2. Okay. Well, which 2 am I gonna miss? What if I did it again with another degree 3? I'll get a new 3 solutions, right? That's fun. Yeah, so can I just do this and get all of them? The answer is yeah, you absolutely can. The reason for this is that the monodromy group of such a homotopy is the full symmetric group, and we'll get to that later. So the idea that you should be thinking in your head is that there is no inherent bijection here. There's no unavoidable canonical bijection here. In fact, any function can happen, depending on which gamma you choose. Specifically, depending on what path you choose here. Homotopic paths will give the same function for people who know what this means. Okay, cool. Any other questions? Great questions. Okay, so the other thing that's important is, let's think, anywhere here, we have some polynomial, right? Of degree d distinct roots, and I know them all, they're the xi's of that t value. So, this is some constant times the product of x minus xi of t. Polynomial is a one variable factor completely over complex numbers. And as t goes to 0, some of these roots might go to the same place. And that would give me multiplicity in these factors. So not only, if I have distinct roots, am I getting each root exactly once? If I have a root with multiplicity k, there will be k paths going there. So you can get at the multiplicity information. Not just the variety of f we can see. Okay, I think I'll take more questions. I just wanted to say those. So that's a really fundamental result here. All paths are reached with the appropriate multiplicities. Okay, we'll end early. So we can have 10 more minutes of coding. I promise it'll be worth it.